Okay, and then I'm going to, oops, share my screen. That's what I want to do. Okay, so I'm going to open up a new Excel sheet for you guys. And I think that assignment 2 is a pretty good way to go over like the refrigeration and the freezing problems that are going to be on the test. And then I think the only like kind of new thing is the microwave problem. And so, yeah, we can go over that. So for microwave, one of the things you're going to need is the dielectric constant and the dielectric loss factor. And those are things that are just inherent to a material type, like a food type. So he went over in class the carrot. So like a carrot's going to have a different one from, you know, a potato or a piece of pizza or something like that. So they're all going to have different, those are the, I think it's sigma prime and sigma double prime. I can't remember the actual Greek name for it, but so if you go to like this, or it might be in our book somewhere, down here, there's a graph of frequencies, the constant, and the loss factor. So what we're going to do is go over the carrot. So for a carrot, we have frequency, dielectric constant, and then dielectric loss factor. And you guys can tell me at any time to stop or explain or whatever. Just let me know. So for this carrot at a frequency of 915 and 2450, the constants are 73 and 72 for the different frequencies. And the dielectric loss factor is 20 and 15 for the two different frequencies. So it depends on the frequency as well. So like if your microwave is running at 915 megahertz, your dielectric constant and dielectric loss factor are going to be different. And I think he covered this in class, but the dielectric constant is like the ability for the food to absorb the energy, and then the dielectric loss factor is the ability for the food to disperse that energy throughout the rest of the food. And that's important when trying to measure the penetration depth of the microwave. So the equation you're going to be using is, I wish I had a way of writing it up, but I think it might be in here. Yeah, okay. So Z is the depth, lambda divide by 2 pi, and then that big fun equation. But basically what you have to do is convert frequency to lambda, because that is what this equation uses, is lambda, otherwise wavelength. So since this is in megahertz, so frequency in hertz is going to be equal to this times a million. And then to get to lambda, it's the speed of light equals lambda times the frequency. So the speed of light is, it's like 2.99 times times 10 to the 8th, I'm pretty sure. You might have to, I'm just going to go with that for now, but I'm pretty sure that's right. So frequency is going to be equal to so since it's, I'm going to try to do a little bit of everything in this. It's going to be hard, but so so speed of light, that is not what I want. Speed of light equals lambda. I'm pretty sure that's a nu. So we have nu and we have speed of light. So c over nu equals lambda. So all we have to do is divide speed of light by the frequency, and that is the lambda. Okay, and then so to find the tan delta, or the delta number basically, so we go back to this equation. So this relates the dielectric loss factor and the dielectric constant together, which we have both of here. So we can find tan D by dividing the dielectric loss factor by the dielectric constant. And then we can find, I'm pretty sure, okay, that's tan squared. Okay, so we need to find D, I'm pretty sure. So we can say okay. And then since we have that, we can start plugging things into this big Z equation. So I kind of like to start with like different orders of operations and kind of divide it down. I think Dr. Malakarjunan really likes to have everything in like one cell, but I think that leads to a lot of mistakes, but you guys can do it however you want. Maybe we don't need to find D at all. I'm thinking we don't need to do that because I'm pretty sure it would just be this squared. Oops. Okay, so that's everything like in the parentheses here. And then
wait, could you really quickly show what was in cell 3J really quickly again?
Yep. So that's just 1 plus is the tangent squared of d. So this is tangent squared of d here in I. So 1 plus that, and then the square root of that, and then minus 1. So that's this part of the equation here that's in parentheses. Okay. So then we're going to multiply by the dielectric constant, which is all the way back over here. Let me just move this. So that times what was in the parentheses. I'm just going to call this denominator. And then equals 2 divided by that value. And that's what's in the brackets. And then we're going to take the square root of that. Okay, and now we can multiply this. So now we can find lambda divided by 2 pi. So we can go back to where our lambda was. Okay, and then we have this times that. And that should be our answer for, so for the two different frequencies, we have that. And I think the dimensions are going to be in, let me just make sure. I don't know what the units are in. I don't know if it's meters or centimeters. Okay, that makes sense. Okay, so for this, I think so you have to convert the meters into centimeters. But I don't know if 64 dielectric loss, is that, yeah, I think we just need to convert from meters to centimeters. So it's a quick change, go back to frequency of, speed of light, because speed of light is meters per second. So to change it to centimeters per second, you would multiply by 100, which is the same as that. And then that should be, did I do that wrong? Nope. Okay, yeah. So that is your penetration depth in centimeters. And on the test, I think I'm probably gonna be grading it again. So I would say, like, if you have the equations out, I'm pretty lenient about, like, if you mess up a number or something, or if you say that the speed of light is 3, 3 times 10 to the 10 centimeters per second, or, pi is like 3 as well. It's just about, do you know what the concept and how to apply the math to it is what we're looking for. So does anyone have any questions about this?
I know for him, like when he did it, his answer ended up being like 448, not 44. And
Okay.
then like 220.
Okay, so it looks like I'm off
So I
by
don't
a
know what
factor.
happened.
Yeah, I can, let's see, I wish he didn't send me the Excel spreadsheet that he did, but he sent me the video at some point. I don't know where I put it. But I can go and review if that's helpful to review, and then like send you guys all an email telling you know where I went wrong, because it looks like I'm just off. Either one of us was off by a factor of 10, because that would have been 442. And then that's just a difference of probably, I rounded pi. So I can do that, unless you want me to go try to find it right now.
So one thing I was wondering is like when you go to your lambda 2 pi, can you click on that like 51?
Yeah.
Do you have to put parentheses around the 2 times pi?
Not technically, no, because it doesn't matter. Wait,
Because
actually,
mine is different.
yes, yeah, okay. It shouldn't matter.
I didn't think it should either, but I know that mine did. Yeah, I don't know if it
Yeah,
changes it later or not.
okay, it does. So, okay, yeah. Oh, and he must have been using. I wonder what units he was using. Maybe he was using micrometers for like microwaves or something. I don't know. But yeah, that makes a lot of sense. Thank you. So yeah, just remember to do that. I'm honestly saying, like, if you guys show your work and stuff, and you make a mistake like that, it's a lot better for me to know that, and I can be more lenient knowing that like you had everything up to that point and it was just a matter of parentheses, rather than being like, you know, here's a number that's random and I don't know where it came from. So just show your work. Yeah, and then units too. Like if you say centimeters and he wanted it in meters, then that's, you know, same thing really. Do you guys want to move on to the next problem, or do you have any more questions about this one? Yeah, so if you're submitting a spreadsheet, just upload the file, have the numbers. Labeling them is nice. You don't have to label them, as long as I can, like if you just did everything in one cell, that's okay, just as long as I can like follow where your math is. That way, it's just if you have a wrong value somewhere, I can see where it went wrong, and yeah, still give you points for the stuff that you did right. Okay, any more questions about this one? Okay, I'm going to move on to the next one that he talked about in the review session on Friday, which was, I believe, was it refrigerating or freezing? I think it doesn't matter too much, but I can go over refrigeration. So a lot of people in the homework did it different ways, and there's a couple different ways to do it. And they're all totally valid. You get points for whatever one you want to do. But so going back to chapter 6, one of the ways you can do it is by using one of these phase diagrams. So you can find where the pressure is. Give me a second, and I can do this. So like on this one, you can say, okay, the pressure is, ooh, sorry, I was moving around really fast. Zoom in a little bit. My computer's not reacting super well, sorry. But so we have like H1 here, H2 and H3, and you can find those by knowing what the pressure is and then knowing what temperature you want. So these lines here that go kind of up and down are going to be the temperature. I think in these are percentages, but it's the same sort of idea. So you're given the temperature and you can find the pressure in the appendix at that temperature. So like, I think this one's for ammonium, but let's say, you know, at 45 degrees Celsius, you can find the pressure and then you can find the enthalpy for that, and then use those values in your equation for H1, H2, and H3. The second way you can do it is these give you, they're going to give you, I think it depends on the problem, but it'll give you 2 of the enthalpies and you can use that information to find the third enthalpy. And it's just a matter of figuring out where the enthalpies belong on the refrigeration kind of, it's not really a rectangle, but trapezoid, I guess. And then the third way to do it, which is the way that Dr. Mallikarjunan was doing it, and I think he kind of wants you to do it, but I don't think it should matter that much, is using all of these coefficients. And we can go through that. So this way using the coefficients is going to be the most precise. Doing the kind of eyeballing on the graph is going to be the least precise. So, but you know, like in a work environment, finding something that's like general is going to give you a good idea. And if you use the same values for the entropy, finding something like COP isn't going to matter because you're using those same values anyway. So it's just a ratio. Okay, so I wrote down, I thought, ones he did for class. Maybe I didn't. I need to find the video, or we could just go off of the one from your assignment in assignment 2, because I don't have those exact values, but it shouldn't be. Actually, I'm going to stop sharing for a second and then. Good. Okay. Okay, yeah. So we'll just go off of the homework assignment if that's okay. They're all going to be pretty similar, and once you have like an Excel spreadsheet like this set up, it's pretty easy to just like plug in a number and go with it. So unless anyone has objections. Okay, I'm gonna take that as a no. So these basically you can just copy and paste. They're values that are in your book. They're oops, I don't want to do that. They are up here. So for different refrigerants, you're going to have different values, but you're going to find all of these different coefficients and type them out into the Excel sheet. So like for, I think what ammonia is 134 or 717, I think it's 717. You would follow this column down as all the variables. So that's here in this little chart. And which one was it? There was one that had an error in one place in the book. But again, if there's like an error in the book or something and you copied that number down and you've used it, as long as you have the equations that show that, you know, that's what you did, it doesn't matter if that number is wrong in the book. That's totally fine. So let's say we have T evap and then T conditioner and DT cooling load. So these are all just labels. Okay, and so basically what he did and what you can do too is go back to the textbook and then down here somewhere, there's actually like a printout of an Excel spreadsheet that you can, yeah, so right here. And this is basically, it tells you the equations, it has it all like written out there, and that's basically what you follow to set this up. And I can go over that with you guys if you want. But it's just basically a lot of typing in equations. So 15 minus 8. So you'll be given like the cooling load and the temperatures of what you're supposed to be finding. Okay, and then comp is going to be So basically, you just kind of follow that down. You guys want me to go through typing out the rest of these?
Where is, oh, it's on page 36. Is that what I'm seeing? Like the example spreadsheet? Okay, thank you.
Yep, yeah. So yeah, you can just, I mean, I figure we can spend our time doing something else if that's, Kumar modified this problem for the problem he did in class. Can you remind me how he modified it?
That's what I'm a bit unsure of. I know he did, but I was just kind of, I don't know, I got really lost. So I was wondering if maybe you knew or if anyone else knew. I don't know.
Okay. Oh, sure, 80%. So that's when we're talking about the efficiency of the compressor. So if it's like 80% efficient, so that's going to be 0.8. So basically, we're saying that the compressor is going to have to put in basically 20% more work to be able to get the same like amount of cooling. So once you find Q condition, so let's say, you know, it's like 3, you know, whatever it's going to be, then with the efficiency, it's going to be divided by that. So that's how much work the condenser has to put in to get it to cool everything or condense everything. Does that make sense? Yeah, exactly. Basically, yeah, so you're going to divide the, so this is like the hypothetical perfect energy. In a perfect world, energy transfer is 100%, but it's not. So if we're trying to make some ice cubes and it takes 3 units of energy to make those ice cubes, theoretically, it's going to take more energy to actually make those ice cubes because the refrigeration system isn't as efficient as perfect world. Yeah, exactly. Some energy is going to be lost, and you have to make up for it in putting in more energy. The flow rate is different. So the flow rate, you do need the flow rate to calculate the energy required. Moving all of my Zoom stuff around. So for the flow rate, that's, so M equals, I wonder if I can just copy, yes, there we go. M equals Q divided by H2 minus H1, and M is the flow rate. So Q is going to be the refrigerant load, and that is just going to be a kind of basic equation. So we have our cooling load here. So that's saying, basically the cooling load is saying we have 15 pounds of stuff in our refrigerator. And that's how much stuff we're going to have to cool down. So we take 15 and we multiply it by, I believe it's just this. Yeah. So 3.5168. Oops. So it's just that you have a certain amount of kilowatts, so energy, well, energy per second. So I think a watt is a joule per second. So that's the energy flow rate, basically, is how much refrigerant you have times the amount of energy per second that's going in. Does anyone have any more questions about this problem? I can continue working through it if you guys want. Otherwise, we can move on to any more questions. Here for whatever you guys need. Yeah, the spreadsheets are confusing. I would say you guys are gonna have a week to work on this, but if you want to like jumpstart it, I would suggest just kind of setting up, you know, if you already did like a spreadsheet for assignment 2, you can reuse that. But setting up just an Excel spreadsheet using that this picture here, page 36. I think it's figure 6.3, 6.4 of chapter 6. Just setting up those equations, and then you can plug in, you know, the new temperature and refrigerant load and the efficiency rate. And then, yeah, you should be pretty straightforward. I think it's a little bit harder for the refrigeration problems, but it's always a good idea to kind of check your your answers against what you think would actually happen. Q value of 47. So that was just me using a cooling load of 15 tons. And then so you multiply 15 tons times, it's like the energy it takes, and it's like kilowatts per ton. And that's just consistent across the board. That. Okay, yeah. So 1 ton of refrigerant is equivalent to latent heat fusion of 1 ton ice melted in 24 hours. So that is 3.5168 kilowatts. So that's for 1 ton of refrigeration. And that's the same across the board for every refrigerant, everything to find the flow rate. And then that's just multiplying that value by the load that you have. So I just picked 15 tons for that. And then with that, I think another thing that's really easy to mess up sometimes is units. So just take into account, like, so this is 3.15, or sorry, I keep doing that, 3.5168. I probably did that here too, yeah. There we go. That's probably a lot better. So this is in kilowatts, and a watt is equal to a joule per second. So if you're trying to find the energy in joules, then you need to convert from watts to joules per second. Or like, I think this was mostly for like freezing time. So if you have watts and you're trying to find the energy in the amount of time, then you would convert to joules. Does that make sense? How did you get Q for calculating M flow? So yeah, so that's just the load. Q is just the load of the refrigeration. So that is the tons of refrigerant you have. So in this case, in this problem, it was 15. So you're saying you have 15 tons of space, basically, to be refrigerating. So think of like a giant walk-in refrigerator. You have 15 tons of stuff that needs to be refrigerated. And then the amount of heat per time is going to be this 3.5 value. So it's just this simple, you know, the amount of stuff you have times the energy, basically, and that's how you get Q. So the only thing that's going to change for Q for you guys in this problem is this like 15 value. So it might be 8 or 10 or 1 or whatever. But you're always going to be using this 3.5 value. Does that make sense? Does anyone have any more questions about this problem? Okay. Do you guys want to do a problem for Planck's or Fam's equation for freezing? Okay, we'll do that then. If my Excel spreadsheet wants to cooperate. Maybe not. Okay, there we go. So again, if you have, you know, a spreadsheet from, oh, I will point out too, sorry, quick, go back to the first refrigeration problem. So you do have to pay attention to the energy that you're calculating. So I think it's pretty common to just kind of mess up and say, oh, I'm calculating the compressor, but use the wrong equation. So for the energy of the evaporator, that is H2 minus H1, and then Q cond, which is the condenser, is H3 minus H1. And then since technically the compressor is changing the pressure, you can't say Q, it just is a thermodynamics thing, but if you say Q, it's fine. I'll know what you mean, just letting you know. But technically it's W, it's the work required by the system to compress it. So the work of the compressor is, see, like he just put down Q. A lot of people use Q. Oops, I'm sorry, that's confusing. It's 3, not 2. Work of the compressor is H3 minus H2. So those are the different ones. And if it says you have to find the Q of the energy of the evaporator, it has to be H2 minus H1. You can't use H3 minus H1. It's just going back to, let me see if I can find, well, going back to one of these charts. Okay, so like this one where, so from E to A, you're evaporating. Yeah, evaporating, and from A to B, you're compressing, and then from B to D, you're condensing. So if it's asking you to find the energy of the evaporator, it's H2 and H1. If it's compressing, it's H2 and H3. And if it's condensing, then it's H3 and H1. Does that make sense to you guys? Okay. I'm gonna assume that's a yes. But yeah, that was just something I noticed some people in the homework doing, where they used a condenser instead of a compressor. So just something to look out for. Okay, so for freezing, we can do Planck's equation first. Okay, so pretty much the basic thing you need to know is this equation here. So freezing time is equal to the density of the food times the latent heat, divided by the temperature of the freezing air. Oh, sorry, temperature of the food at frozen temperature, and minus the temperature of the air. And then P and R are the different coefficients for the different shapes. So like these values here, slab and cylinder and sphere. X in this situation is the distance, I think, right? Yeah, 5 centimeters. So that'd be 5 centimeters. H is the convective heat transfer, and K is the thermal conductivity of the frozen product. So basically, you can kind of just plug and chug these. With L, the latent heat does depend on the moisture content. So if you have the latent heat here, yep. So I think it's pretty common to have that. And I think the reason, yeah, so that's in kilojoules. So then if you wanted to convert that to, so if you want to include like the moisture content, you would say if it's 85% moisture, or I guess not 85% moisture. Or I guess you could say 83%, 85. Whatever the moisture content is, I'm sorry if I'm being more confusing than helpful. But so you'd say the latent heat times the moisture content. So in this case, we're going to say 85. So it's times 0.85. And then to convert from kilojoules to joules, which you have to do for this, it's times 1,000. So then you would have this as your latent heat in joules for the product you're working on. And that is L in this situation. So if we're given this problem like 7.3, we have the thickness, which is going to be X in this equation. We have the air of the temperature, the temperature of the air, which is TA. The product moisture, the density, the thermal conductivity. Oops, I should do this differently. Thermal conductivity, initial freezing temperature of, so that's TF, and the convective heat transfer is H. And you can organize these however you want. You might want to put like TA next to TF or something, but it's up to you guys. And again, this is in centimeters. That's good to remember. And if you're going to use like 1 unit of temperature, you can keep that consistent throughout. It tends to make more sense if you use Celsius, especially if it's given in Celsius, but for like this thermal conductivity, I think you do have to convert to Kelvin. So we're going to say 0.73 for moisture content. TA is going to be minus 30 plus 273. In centimeters is 5. Might be easier to do. I'm going to convert that to meters right now. And then rho density is 970, and that's in kilograms per meter cubed. Okay, is thermal conductivity, which was 1.1. That's in watts. Wait, what did I do? There we go. Watts per meter Kelvin. GF is and then H is 5 units, and that are watts per meter squared. Oops, sorry, watts divided by meter squared times Kelvin. Okay, so does this setup make sense to you guys? I assume that's a yes. If not, just let me know if you have any questions. So I'm gonna kind of do this how I would do this question. I would say I want to find the right side first. So the right side that we're multiplying. And I'm gonna do the numerator first. So that is just going to be this latent heat that we already multiplied by our moisture content. And remember that this latent heat is just the number you have, and I converted it to joules. So it's 333 kilojoules, so that's going to be 333,000 joules, and then multiplied by the moisture content. So we take that and we multiply by density. And then you can say right denominator is going to be equal to TF minus TA. And that is in Kelvin. So then we can just say the right side is going to be equal to that divided by that. So that's our value. And if we're keeping track of our units, that's going to be in joules times kilograms per meter cubed and all over Kelvin. So I know that's kind of a mouthful of a unit, but we have that. And then we're going to do this second part. So I'm going to say the left first part, and then the left second part will be later. So that's like the first addition. So remember, P is going to be from this, and that's also in your book. And those are just the values we use. So like if we were going to do, for this one, a 5 centimeter diameter beef sphere, like a meatball, that would be different. We'd use 0.166. Since we're doing a slab, P is equal to 0.5. So we have equals 0.5 times our density, not density, distance. Thickness times that, and then divided by h. There we go. So that's that part. And then we're going to do the left second part. So the first thing I'm going to do is take the square of this and put that in parentheses. And then I'm going to multiply it by the R value. So that's again over here. So that's 0.125. And then all of that divided by K. And so now if we want to do our units again, we have meters and then density. So the meters are going to cancel out for that. I'm going to do this. Okay, I'm just going to move to a different spot then. Okay, so we have and then since this is on the bottom, we can flip this. And then those cancel out. And we're left with kg times K over watts. And it should be the same for the second half because we're adding them together. The units need to be the same. But so then we have all of the separate parts. So we can add these parts together, this part and that part. And then we're going to multiply that. So this is the left-hand side. And that is our answer. And that's going to be, I think, in seconds. And then you can convert it to, oops, I don't want that. I want this. Nope, I did something wrong. I think my latent heat is different. Oh yes, because I used 0.85 instead of 0.73. So now our answers are the same-ish, and that's close enough. The right numerator and denominator. Yep, so right numerator is this, and I'll make this bigger so that you can actually see it. I'll kind of zoom out a little bit. So the right numerator is just going to be this density times the latent heat. And then the right denominator is going to be the temperature of the frozen product minus the temperature of the air in the freezer. So yeah, again, so just keeping track, you don't have to go and find the actual units. If you feel comfortable with just kind of plugging and chugging, you can do that. I always like to do units because I like to double check and make sure that I'm in the right units, because if I get something weird, like if this was my answer, if I had, 44,000 kilograms per times Kelvin per watts, I would be like, I don't know what that unit is. I was supposed to get something in time, probably seconds. How do I get to seconds? Where did I go wrong? And figure that out. But so in this case, we're going to have that as what was in the left side, and then the right side, as we determined. So we're going to multiply this by joules times kilogram per meter cubed and divided by Kelvin. So that's going to cancel out. And then we're going to have kg over watts times joules times kilogram per meter cubed. Did I do something wrong? No, okay, because there is something really weird with, no, I must have done something wrong. I know what I did wrong. It's because this shouldn't be that. I put density in there, and that is just P, and it's a unitless value. So I'm sorry if I'm being more confusing than helpful, should just be meters divided by watts, meters squared times Kelvin, which is going to be meters times meters squared times Kelvin divided by watts, and that's going to be meters cubed times Kelvin divided by watts. So now when we're introducing this new part, which is joules times kilograms divided by meters cubed over K. K's still cancel out. Now meter cubed cancels out. And a watt is, where am I still missing a kilogram from? Maybe it's something in the latent heat, joules per kilogram times density kilogram per meter squared. Yeah, that's probably where it's coming from. Yeah, so those are already canceled out. So you're just left with joules over watts. And then remember that a watt is equal to a joule per second. So then we have a joule divided by a joule per second, which is equal to a second. So yeah, you can kind of get caught up in a few different places, but just try to keep chugging through it, I guess, and you'll eventually get to the right answer. So if you leave it in seconds, that's fine. I always prefer putting it into more understandable units. So like we can put it into hours by dividing by 3,600. So that's 12.2 hours. And that gives you a better understanding of what that answer means rather than just 44,000 seconds. But yeah, so that's Planck's method. Does anyone have any questions about this? Does anyone want to go into Pham's method next?
Yes, please. I don't know what the heck that is.
Okay. Yeah, so basically the difference between Planck's and Pham's is just, you know, like if you think about, if you've taken calculus before and you're thinking about calculus and you have, you know, your blocks of stuff under the curve. Basically what we're doing with Planck's versus Pham's is saying, oh, I'm going to do it, you know, this way where, you know, the left side meets or the right side meets, and then, you know, the other way. So some are going to be better. They're going to fit the way to find the actual time it takes to freeze better. It's just, it's mathematical modeling. So they're both ways to measure the time it takes to freeze. They're just different equations. So we will go over Pham's. Where did my Excel spreadsheet go? I have too many things up. I'll start a new sheet for that too. Okay, so we're gonna go over Pham's. And I'm gonna pull up that again. I'm gonna go this, and if it's okay with you guys, I'm just going to do this problem again that he did. Okay, so for this problem, the equation that we're using is t equals, and I'm not going to put an equal sign because then Excel gets weird and thinks that I'm doing something weird. But so then it's d divided by EH times, in brackets, delta H. And so I'm going to do, gosh. So delta H1 divided by delta T1, and that's in parentheses, plus delta H2 divided by delta T2. And that's n brackets, and then that is multiplied by 1 plus n bi, so that's the bio number or biot number, divided by 2. So things that we are going to need are all of these values really. And I'm going to start down here because I know that there's some equations for these H and T's as well as the biot number. So I'm going to put those in just as this. And then E. So like over here, you can see where all of those different variables come in. 1, 2. Okay, and then we're gonna go back into I, A, C. I'll go through all of these in a second. I just wanted to type them down really fast. Okay. So if we look at the problem, we can start filling in some of these things. So we're doing a meatloaf with a moisture content of 85%. Some moisture contents here, so we're going to put in 0.85. Following dimensions: length, width, and height. So for this, with Pham's equation, the most important thing to remember is we're looking for the distance to the center of the product. So if we're talking about a meatloaf, it's the center of the meatloaf, strawberry, center of the strawberry. And you find that by finding the smallest dimension here and then dividing it by 2. Because if you think about it, the height is going to be 10 centimeters, so it's something like that. But then to get to the middle of it, you divide by 2, and that will give you the middle of the product. So for this, X, I think, is what we're doing for, or he's doing DC. So 0.05, and these are all in meters. And then put down those. And again, just keeping track of centimeters versus meters. So in the problem, it says centimeters. A lot of times we want to use standard units. So that's the Kelvin or Celsius, depending on the problem, which is confusing, but Kelvin's always good. Meters, kilograms, joules. Those are pretty, I think those are pretty much it for this class. So then we're in the problem. Convective heat transfer coefficient is 40 watts per meter squared times Celsius. So that is, again, H, just like, I think it's just as it was in, yes, so H is the same, or sorry, I said that wrong. Convective heat transfer. Yeah, okay, so H is the same in both Planck's and Pham's equation, and it's the convective heat transfer coefficient. So that for this is 40. And that is in watts per liter. Okay, and then the initial temperature of the product is 10 degrees Celsius. So Ti is 10. Air temperature is -40, so TA is -40. Initial temperature, oh, we already did that. And the final temperature of the meatloaf is -18, so that's TC in this case. Thermal conductivity is 1.5, and he did that as KF. And that's in watts per meter. Specific heat of the unfrozen meat is 3.4. So that is here. Density, since we're here, is 1020. And that is kilogram per meter cubed. Specific heat of the frozen meat is 1.9. And again, that's going to be in kilojoules per kilogram times C. Wait, no. Yes, sorry. And then what did he do for row U and row F? Oh, they're just the same. I don't know why he included those. It doesn't matter. I guess it does matter because sometimes you'll have different densities as things freeze because ice expands. But typically you wouldn't see that much expansion. The thing that matters more is the specific heat of the meatloaf, whether it's frozen or unfrozen. So again, we're going to kind of go through this. Oh, I should put in the different betas, I guess. I seem to remember that. Okay, yeah. Okay, so I'm going to start with TFM. I'm actually going to move this up so we can kind of have it all in one page and do that. You still see if it's really zoomed out? Okay, so I'm going to put those there. So I'm going to start here with TFM. So TFM is going to be equal to 1.8 times, 1.8 plus Okay, so for this one, for finding TFM, these values 1.8, 0.263, and 0.105 are that's just part of the equation. You don't have to find those values. And then it's the TC and the TA. So the TC is the temperature of the air. or sorry, the temperature of the final freezing and the temperature of the air. So now we have TFM. We're going to find the Biot number next. So the Biot number uses, again, the shortest distance to the center of the meatloaf. So it's that distance. Oh, it's going to be stupid. Okay. Okay. No, that's not good. Where are they?
What does the Biot thingy represent?
So that is just, hang on a second. I wrote a bunch of stuff down. I guess I didn't write that one down. But it is, mention this. That is a good question.
I mean, it's okay. It's a mysterious number.
Yeah, it's just something we have to figure out, created by someone who's a lot smarter than me. But based on, so it's unitless, and it's the ratio, it looks like it's the ratio of the thermal conductivity. Is that right? Thermal conductivity? No. Specific heat. So it looks like it's the ratio of the specific heat, and it throws in the distance of the meatloaf as well to the center.
Yeah.
So it probably is just sort of a ratio of, if we think about freezing, you guys probably saw this in your freezing labs. Let's see here if I can find it. I saw it earlier. Okay, so it's probably a ratio of how fast, this curve or this whole section from start to finish is happening.
Mm-hmm. Okay.
Interesting. So it's going to be. Yeah, there we go. So the ratio of it when it's not frozen and then frozen and multiplied by the distance of it. So yeah. Okay, so we have Biot and TFM. Beta is, I don't remember needing to find beta. Is for H. Oh, it's for finding the specific heat. Or no, it's not finding the specific heat. Let's use beta in. Oh, it's for finding E. That makes sense. Okay. So we'll get to that in a bit. Let's do the H's for now. So for H, H1 is the, again, I can't do an equals here, so it's a little weird, but it's the density, so rho, times the specific heat unfrozen, so that's Cu, or in this case, he put CPU, and then times that by Ti minus Tfm. So in this case, H is going to be equal to the density here times this value, the specific heat, times Ti, so 10 degrees, minus Tfm, which is here that we found. And he converted to joules, which is a good idea. So here we have kilojoules, and it doesn't matter if you do it here or here, just as long as, again, you keep track of your units. So here we can multiply by 1,000, and that will get us joules. So then this is going to be H in joules per meter cubed. Okay, and for H2, it's pretty much the same thing, except you're doing the, you're doing it a little bit different. So I'm going to move these over so it's a little bit more clear. So now H2 is equal to rho again, but this time it's the rho of the frozen, which again, like we talked about, is the same as the rho of the non-frozen. In brackets times LF, which is the latent heat, plus CF, which is the specific heat of the frozen. So over here, again, he put CPF. So CP is also kind of a an abbreviation for specific heat. Some people just do C. So it kind of depends on where you are, but times TFM minus TC. So that's what we get for, oops, let me do that. So that's what we get for the H2. So rho times LF. Again, LF is just 33.332 times the moisture content. Pretty sure that's how. Moisture content. Oh, yeah, because it's down here. Yep, okay. So, sorry, just checking my work. Okay, so that's density times latent heat times the moisture content, because that's important, times CF, which is 1.9 here, and multiply that by TFM minus TC. And again, I didn't multiply by 1,000, but we will, because this value over here was in kilojoules and we want it to be in joules. Okay, so now for the T's, I'll put T1 here. T1 equals Ti plus TFM divided by 2. So these should be in parentheses. And then these are in parentheses as well. Minus TA. And then T2 is equal to TFM minus TA. Okay, so now we're going to get on to the E. And like I said, you have to find beta 1 and beta 2 for that. And remember, the E is important up here for this D divided by EH. So beta 1 is going to be equal to, so it's going to be the shortest distance that you use times one of the dimensions. So in this case, it's the width. So width times height, basically, is what we're doing here. Oh, sorry, divided by. So sorry about that. I misspoke. Width divided by height. I'm just not doing it right enough. I don't know why I'm getting a different value than him. Oh, because I did it in reverse, that's why. There we go. Okay, and then for beta 2, we have, again, this time it's going to be the length divided by the height. So in this case, it's important to remember to multiply this value by 2 because we took, we divided it by 2 to get the radius basically of this, which like I said is important for FAM's method because you're wanting to find the middle. But these values are about the total dimensions. So just remember to, if you put in the divided number here, like I did, to multiply by 2 here, or if you put in the full number, like I didn't do here, you have to use the divided number in your biot. And I think it's also for TFM, no, just for biot number. Okay, so then, okay, so now X is just this long equation. That's not a lot of fun, but these values again are just values that are in there and aren't going to change, part of the equation. Oops.
Mm,
Hmm. Okay. Okay, so once you have x1 in, it's the same equation for x2, except using beta 2 instead of beta 1. So everything else is the same. And then for E, we're doing E1. Okay, and again, E1 is the same as E2, but you just have to go in and make sure that X2 and B2 are being used. Okay, and then E is 1 plus E1 and E2. Okay. So now we have all the parts of this main equation together. Yep, just making sure. Okay, so now we can start putting together and finding T. So I'm gonna get rid of that and just put T right there. And again, I kind of like to break it up. So I'm gonna say the left side, and then I'll do like the middle and then the right side. So the left side is D divided by EH. So if we go and find D, I think that's, we did it differently. Okay, I'm pretty sure D is, yeah, shortest distance to center. So D is this. D divided by E times H. That's a convective heat transfer, so that's there. Okay, so that's that, and then we have the middle. And so since we have two parts in the middle, I'm going to say the middle left, and that's going to be equal to H1 divided by T1. And then we have middle right. That's going to be H2 divided by T2. And then we have the right, which is 1 plus the Biot number divided by 2. Okay. So now we just multiply all those together. Oops, sorry. You don't multiply all those together. My bad. Because I'm going to middle total equals the total of these. And now we can multiply this and this and that. And so that is our value. And I don't know why. Ah. So I did something wrong. And even if I didn't have this guide here to tell us, you would probably say, oh, 62 hours is a really long time to freeze a meatloaf, so might have done something wrong. The next step I would take is looking at my units and seeing if they cancel out. Or I guess even before that, looking at Excel, because sometimes Excel does weird things. Might be, I think, might have written down the initial equation wrong. Nope. Okay. So probably somewhere my units are wrong. Oh, I think I know where I went wrong. I should have added this instead of multiplied. So that will give me a very different answer. And now since I've linked everything together, this should be the right answer. So we're going to divide that by 3,600 and we get 3.726, which is the correct answer. So like if in this situation, like if you're in a similar situation as me, where you know, like this value was really off because I multiplied instead of added, like if you have this equation here, you know, written somewhere, you know, you could take a screenshot, whatever, and you did that, like, you know, minus a very small amount of your points, because it's like you thought everything through, you just made one mistake. It's totally fine, even if you didn't get that right answer. Again, it's always best to look back and make sure that you are getting something that sounds reasonable. I know it could be hard if like you make a mistake and you get something like 5 hours, like that sounds pretty reasonable, or, you know, 2 or 1 hour is pretty reasonable. But if you're getting something like 10 seconds or, you know, 30 days, you know that something's going to be a little off. All of these problems are, you know, relatable to the real world. We're not talking about theoretical. I mean, it is theoretical, but these are all going to be very applicable to what you would expect from like your home freezer. So yeah, just remember to pretty much write everything down. If there's a mistake or you carry a number weird, then I can try to give you points for it. Does anyone have any questions about this problem? Does anyone have any other questions about things that we went over in class, or just anything?
So we'll, oh, sorry.
Go ahead.
So will Dave's part have like calculations, or will it be just like theory stuff?
It's just theory. Yeah.
Okay, so Kumar's part is the calculation. Okay, that makes sense.
Yeah, Kumar has 3 calculation problems and 2 like kind of theory problems as well. I am not sure. I can try to work on those. The question is when short lab reports and presentations will be in the grade book. I wasn't grading the short lab reports, so I can see if I can help speed that along and try, but yeah, I don't know. And then as far as presentations go, I don't know about that either. You have another presentation tomorrow, right? Okay, yeah. So I don't know. I can try to help speed things along, but I sent Dave my evaluations for the last presentations he did, so I think he's working on those grades. But yeah, I mean, if there's any other questions about anything, I don't mind staying a little bit later if you guys want to go through other problems or anything. You're welcome.
Thank you.
Yeah, of course. And I don't mind sharing this with anyone who wants it either. So
yeah, I think I just have to work on making these spreadsheets.
yeah,
Work. Yeah.
yeah, because as soon as you have the spreadsheet layout all set up, you can just plug in numbers and it's beautiful. And you can have the test done in like 3 minutes.
3
No,
minutes,
it's not gonna it's not gonna happen that way, but
Thank you, Kat.
yeah, have a nice night.